Hello everyone, welcome back to my lectures on formal languages and automata theory. In this lecture, we shall discuss about the central concepts of automata theory. As we have discussed in the previous lecture, automata are machines which accept or reject formal languages. Because we are talking about languages, just like natural languages have alphabets, strings, and languages, formal languages also have alphabets, strings, and languages. We therefore need to define alphabets, strings, and languages for formal languages. So let us start with alphabets first. Alphabet. An alphabet is a finite non-empty set of symbols. The symbol sigma is used to represent an alphabet. Now let us look at a few examples of alphabet. The set consisting of 0, 1 is a binary alphabet. The set consisting of small a, small b, so on up to small z is the set of all lowercase letters, and it is the alphabet of the English language. The set of all printable ASCII characters is the alphabet for a few programming languages. This is what is the definition of alphabet for formal languages. Alphabets also exist for natural languages, but in the perspective of the formal languages, this is the definition of alphabet. So now let us move on to understanding strings. A string is a finite sequence of symbols. A finite sequence of symbols, and these symbols are chosen from some alphabet. A string is also can also be called as a word. So a string is going to have a few symbols together, and these symbols are chosen from an alphabet. For example, if we take the alphabet as 0, 1, which is the binary alphabet, strings can be 0, 1, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1. So these are strings from the binary alphabet. So any other combination of zeros and ones can also be a string. So for example, 0 can also be a string on the alphabet 0, 1. Similarly, 1 can also be a string on the alphabet 0, 1. Similarly, 0, 0 can also be a string on the alphabet 0, 1, and so on. So it is going to continue like this. Now let us look at a few important concepts about strings. The few important concepts about strings include empty string, length of a string, powers of an alphabet, clean closure and positive closure, and concatenation of strings. Let us go into the details of each one of them. Let us start with empty string. The empty string is a string with zero occurrences of symbols. The occurrence of symbols are going to be 0. This string is denoted by epsilon. This is the symbol of epsilon. So the string which is empty string is denoted by epsilon, and this is a string that can be chosen from any alphabet. So any alphabet has epsilon as a string, or to be very precise, epsilon can be part of any alphabet, strings made up of any alphabet. So this is what is about empty string. Now we shall move on to the next one, which is length of a string. Length of a string. So as we have discussed already, strings are a sequence of symbols chosen from an alphabet. The length of a string is going to be the number of positions for symbols in the string. So the string has 5 symbols, then the length is going to be 5. Let us look at a few examples. The string 001101. This string has 1, 2, 3, 4, 5, 6 and 7 symbols. Therefore, the length of the string is 7. The standard notation for string, the length of the string W is this. This is the standard notation for the length of the string. So therefore, the length of the string is equal to 7 in this case. Similarly, we have a string 100. Then the length of the string denoted this way is equal to 3. So this is what is going to be the length of the string in this case. So this is how the length of the string is going to be measured. Now we shall move on to the next concept of strings, powers of an alphabet. Now let us suppose sigma is an alphabet. The set of all the strings of a certain length from that alphabet can be expressed using an exponential notation. For example, the length of all the strings is going to be 3. Then I say I know denote it by sigma to the power of 3. Okay, so the if a set has strings of certain length, so in this case, if the length of these strings, all the strings is going to be 3, then that can be denoted by sigma to the power of 3. So we can define sigma to the power k, sigma to the power k, to be the set of strings of length k, each of whose symbol is chosen from the alphabet sigma. So for example, sigma to the power of 0, where the length k is equal to 0, is the only string consisting of epsilon, or the empty string. Let us look at one more example. If sigma is equal to a comma b comma c, then sigma to the power 1 is equal to a comma b comma c. Sigma to the power 2 is going to be all those strings whose length is 2. So therefore, sigma power 2 is going to have 9 strings: AA, AB, AC, BA, BB, BC, CA, CB, and CC. So these are all the strings whose length is going to be 2. This is denoted by sigma to the power of 2, which is a power of an alphabet. If we observe here, there is some confusion between sigma and sigma power 1. Sigma is the set of symbols A, B, and C, whereas sigma power 1 is a set consisting of strings A, B, and C. Because sigma power 1 has strings A, B, and C, and the length of each string in this case is 1. So that is what is the difference between sigma and sigma power 1. So we can observe that if A is used in sigma, it is going to be a symbol. If A is used in sigma power 1, it is going to be a string. Now let us move on to the next concept of, which is clean closure and positive closure. Just now we have defined powers of alphabet. Now the set of all strings over an alphabet sigma. The set of all strings over an alphabet sigma is going to be the union of sigma power 0, which is going to be all the strings whose length is 0, sigma power 1, which is going to be all those strings whose length is 1, sigma power 2, sigma power 3, and so on and so forth. So all these strings together is represented by sigma star. and it is called as clean closure. Therefore, sigma star is equal to sigma power 0 union sigma power 1 union sigma power 2 and so on and so forth. So sigma star is called as clean closure, and it is going to have all the strings over an alphabet sigma. Here we have one more definition which is called as positive closure. Positive closure is denoted by sigma plus. Sigma plus, which is positive closure, is the set of all strings over the alphabet sigma except epsilon, which is equal to sigma power 0. So therefore, positive closure sigma plus is going to be the union of sigma power 1, sigma power 2, sigma power 3, so on and so forth. Clean closure and positive closure are both related to one another in the following way. Sigma star is equal to sigma plus sigma star, which is clean closure, is equal to sigma plus, which is positive closure, union epsilon. So this is the way in which clean closure and positive closure are defined. Now we shall move on to the last concept of concatenation of strings. Let x and y be two strings, then xy denotes the concatenation of x and y. That is, the string formed by making a copy of x and following it by a copy of y is called as concatenation of strings x and y and is denoted by xy. So let us look at a few examples. Let x is equal to 1101 and y is equal to 0011. Then xy is equal to 11010011. So a copy of x, which is 1101, is followed by a copy of y 0011, and this is called as xy, which is the concatenation of string x and y. And the concatenation of strings yx is going to be a copy of 0011, which is y, and 1101, which is x. So xy is a different string from yx. For any string w, epsilon which is the null string followed by w is equal to w epsilon is equal to w. So there is going to be no change when epsilon is concatenated with any string. Therefore, epsilon is called the identity of concatenation. So these are a few definitions that we have discussed, or a few concepts that we have discussed about strings, starting from empty string, length of a string, powers of alphabet, clean closure and positive closure, and finally concatenation of strings. Move on to languages. So now we're trying to define languages. A set of strings, all of which are chosen from some sigma star. Sigma star is the clean closure, and sigma star, as we have defined earlier, is the set of all strings from an alphabet sigma. So where alpha is a particular alphabet is called a language. So now if we try to understand it very clearly, a set of strings, which means a subset of sigma star. A subset of sigma star denoted by L, where all the strings come from some alphabet sigma, is going to be called as a language. Once L is a language over sigma, once L is a language over sigma, then it is going to be a language over any alphabet that is a superset of sigma. For example, there is a language 0, comma 00, comma 000. This is a language over sigma which is equal to the alphabet 0. Now, this is also a language over the alphabet sigma which is equal to 0 comma 1, and 0 comma 1, which is an alphabet, is a superset of 0 alphabet. So therefore a language L, which is a language over sigma, is going to be a language over any alphabet that is superset of sigma. So let us look at a few examples of languages. The set of binary numbers whose value is a prime is a language over sigma 0 comma 1. So all the binary numbers whose value is going to be a prime number is a language over sigma is equal to 0 comma 1. Phi is the empty language consisting of no element, and phi is a language over any alphabet. uh, we if you remember, we discussed about epsilon, a string. Epsilon is a string that is defined over any alphabet. Similarly, phi is going to be a language over any alphabet. So now we shall move on to how we define set former notation. uh, is a very important way in which we define languages. So it's very common to describe a language using the set former. Set former is something that we must have learned in our schooling days. So for example, set of all w such that w is a binary integer that is prime is a language, and this is the definition in the set former notation. Similarly, set of all w such that w is a syntactically correct C program is also one more definition of a language in the set former notation. So this is one way in which languages are going to be defined. Now let us look at an example of language, how problems exist in problems that come under automata theory. In automata theory, a problem is the question of deciding whether a given string is a member of some particular language. If sigma is the alphabet and L is a language over sigma, then the problem is given a string in sigma star. Sigma star, as we have discussed, is the clean closure. So the problem is to decide whether the given string W belongs to the language L, which is a subset of sigma star or not. So therefore, the problems in automated theory can be categorized as membership problems. So when we say that the problems in automata theory are membership problems, we might think that the problems that can be handled by automata theory is a very small set. But actually, any problem that exists in the world can be expressed as a membership in a language or a membership problem. Let us look at an example. Let us look at the example of the problem of testing primality. In testing primality, a number is taken and tested with it whether it is a prime number or not. So what we do is we took we take a set of all the prime numbers, and this set becomes a language. Now any number that we take, we're going to check whether that number belongs to this set or not. and that is the way in which we test the primality. So now the testing of primality has become a membership problem. This is the way in which any problem can be converted into membership problem. So therefore, automata theory can handle any problem that exists. With this, we come to the end of the current lecture. We will continue in the next lectures. Thank you.